Okay. All right, so let's get started. Today's news story. What's up? What's that? Okay. You couldn't hear me? All right. So today's news story arguably doesn't have much to do with 61C. I don't know. It just showed up in my mailbox. I thought it was kind of fun. But, you know, we're seeing this incredible uptick in enrollments in computer science. So at the end of the 90s, we were sort of at this peak of enrollment. And then there was this thing called the dot-com bubble that burst. And then all of a sudden, we were out on the street begging people to come into our classes and, you know, pulling them in. And now we're sort of back up. I'm trying to get the numbers, but we might actually be above the peak. And so we're trying to figure out why do so many people want to take computer science. And I realized that this is it. Basically, free food, which motivates most people. So, you know, so if you get through class and you learn about cloud computing and you learn about parallelism, you learn about, you know, what's going on in the machine so that you can write efficient code. If you're lucky and work hard, you'll be able to get a job at a place that gives you free food, and all they ask in return is you just work like nonstop. So that's what today's news article is about. All right. So today we're going to do two things. We're going to wrap up the discussion of SIMD parallelism at the instruction level, and then we're going to jump into our next big parallelism topic, which is thread-level parallelism. And we're going to spend sort of half of today and then the next two lectures on thread-level parallelism, and then we're going to move on. Okay, so remember, this is where we left off last time, or what we covered last time. We had Flynn's. All right, I need you guys to quiet down a little bit. So we got Flynn's taxonomy. It depends on, you've got two things that you care about. You got data, you got instructions. And for each one of those, you have the option of doing multiple instructions at the time, right? Doing one at the time or multiple at the time, right? So SIMD is single instruction applied to different pieces of data at the same time. MIMD is sort of the massive parallelism where you have lots of data, lots of different data items, and different instructions can be applied to them at the same time. And then we had these other ones, SISD, which was basically no parallelism, and then MISD, which doesn't really exist. Okay, but that was the taxonomy. And then we said, okay, we talked about MIMD at a big scale when we talked about request parallelism and data parallelism in a warehouse scale computer. Then we said, okay, let's spend some time talking about what goes on in an individual processor core. Where do we get parallelism there? One of the places we get parallelism is the SIMD approach, where you apply an instruction to multiple pieces of data. So we talked about that. And basically, the idea is you get these big registers. The architecture we were looking at was using registers of 128 bits. Okay? And you fill those registers with a single instruction, and then you operate on that entire register with a single instruction. And the idea is that's how you're getting parallelism. So if you have 128 bits and you're dealing with 32-bit items, you could take four items at a time. You could do additions. You could do multiplications. You could do all sorts of stuff. So that's where SIMD parallelism comes from. Now, there was a really good question. There were a bunch of really good questions last time. There was one question about, there was a move instruction. So part of when we looked at this one instruction set, the Intel streaming SIMD extensions. And basically, there are a bunch of instructions for moving data, for doing arithmetic, and for doing comparisons. Okay? And the move instructions, all these instructions can be annotated with kind of the structure of the data you're dealing with. And so there are structures for packed single precision floating point. And then there's another annotation that says packed double precision floating point. Right, where single precision is 32 bits, double precision is 64 bits, okay? And the question was asked, hey, when we're moving data, right, so when we're loading data from memory, right, into the processor or into the register, there was a command that we used that was called move aligned or unaligned packed single precision. And the question was asked, why do I care that it's single precision or double precision if all I'm doing is copying 128 bits and moving them into a register? Anyone who asked that question? Somebody over here. Yes, good question. So I did what I always do in this case, which is I swiveled my chair over to one of my office mates who happens to be the author of the book and said, hey, what's the deal with this? And he said, boy, that's a really good question. I don't know. And so we spent a bunch of time looking around on the web, and the best we could figure, so it turns out there isn't an instruction, or at least for the instruction set we looked at, there wasn't a move aligned or unaligned double precision. There was packed double precision. There was only the single precision. And so basically, that was just a lazy way for them to say, hey, I want to move 128 bits. So the original instruction set, if you did the move, it only did 64 bits, and they needed a way to have a move instruction that moved 128 bits. So what they did is they just used one of the annotations for a 128-bit structure, which happened to be packed single precision. So that's the answer. It's sort of a historical accident as best as we can tell. And I'm sure you guys were having trouble sleeping, worrying about that, but that's the answer. So now you know. Okay, good. So let's finish what we're going to do. We got to talk a little bit about how one accesses these SIMD instructions if you don't want to write in assembly language, because at the end of the day, you don't want to write assembly language. And then we're going to jump into the next topic, which is thread-level parallelism. Okay, so the way you're going to be able to use these assembly language instructions without writing assembly language is through a little trick called an intrinsic. And intrinsics are functions that you call, in this case, from the C language, that are basically going to be directly mapped to these underlying SIMD instructions. Okay, so you're writing C. It looks like you're calling a C function, but that's going to get translated directly into one of these fancy SIMD instructions. Okay, and the C compiler knows about them. Okay, so that's how we're going to do it. And they're not particularly beautiful. This is a sampling of some of them. So what you need is a data type. Okay, so if you use with the SSE extensions, right? So you have to include the header file so that the compiler knows about these things. But if you do that, there's a data type you need to know, which is _M128V, which is basically a data type that says I've got 128 bits. Okay, that's your data type. And then if you want to use one of these SSE instructions, there's equivalent calls that you can use in your C program. So here are some calls for doing aligned loads and stores, right? So when your 128 bits line up on a 128-bit boundary, okay? And then there are commands for doing unaligned loads and stores, because remember, this processor isn't a RISC processor. It's not a reduced instruction set computer, right? These guys created instructions for everything. So instead of just telling you, no, you cannot load something that's unaligned, they'll say, sure, you can load it. It just might run a little slower. That's okay. We wrote the microcode for it. It'll work. Okay, so you have loads and store of aligned, loads and store of unaligned. This is kind of a cute one. We're actually going to use this. This basically says load a register, but actually duplicate what's called broadcast across the vector. So we're going to load, say, a 64-bit quantity into a 128-bit register, and the way we're going to do that is we're going to duplicate it. So we're going to put it in the first 64 bits. We'll have a copy, and then in the next 64 bits, we'll have a copy of the same thing. That's a pretty crazy instruction, but it's there for you to use. And then some arithmetic, add and multiply, and there's a whole bunch of these. I think you guys have a lab on this coming up soon, so you'll see these kinds of instructions. All right? Yeah. Okay, so the question is, are there other data types that you can call from these intrinsics? Yeah, there probably are. You're going beyond my knowledge of this language. But yeah, the key thing here is that you need a data type that's 120. You need at least one kind of data type that's 128 bits. Okay? Yeah?
What's the difference between aligned and unaligned?
Okay, so what's the difference between aligned and unaligned? So, if you think about it, we already saw this when we were talking about the MIPS architecture, which is, if you wanted to load or store a word, remember a word was 32 bits or 4 bytes, and so that word had to start on a 4-byte boundary. right? So you could have a word at address 0, and then a word at address 4, and a word at address 8. If for some reason you wanted to have load a 4-byte quantity starting at address 1, that's an unaligned load, okay? And so, take however many bits there are, how many bytes there are in 128 bits, it's the same story here. You've got to be on a 128-bit boundary if you want to be aligned. Yeah? Will unaligned, I think unaligned probably would work. That's interesting whether it would throw an exception. You could try it. The question is, would unaligned work for even if it was aligned? And the answer is there's no reason why it couldn't, but it's probably going to be slower because it's a different code path. Okay? Oh, okay. Got to be on top of this, Dan. Yeah, go ahead.
So if you wanted to use these processes on something that was like not on the pool of 128 nodes,
Uh-huh.
you would have, how would you do it so that you don't use like all 128 bits, or could you?
Okay, so I didn't quite. Are you worried about alignment or the size of the data? Okay, so the question is, if I wanted to do this on things that weren't 128 bits, so presumably smaller than 128 bits, so that's actually what we're doing. Remember, we're going to take these 128 bits, we're going to treat them as we're going to break it into pieces. So we're either going to break 28 bits into 2 double precision quantities, which are 64 bits each, or 4 single precision quantities, which are 32 bits each. So that's exactly what we're doing here. Oh, if you only had 2 floats instead of 4 floats that you want to work on, you just put them in the, you just use those, and you don't worry about the stuff that you don't care about. Yeah. So right, there's no rule that says you actually have to look at the answer to all of these things, right? So if you're only interested in the first quantity, you just look at that one, and the other one can be junk. Okay, one more question. This is actually the simple slide. I want to get through this fast. So one more question, yeah.
But when you do that, like when you're loading that into the register, like let's say you want the first bit.
Uh-huh.
Load it. But you also get 2 others, which possibly could cause a segfault.
Okay, so the question is, could you get in trouble with a seg fault if you're loading some? I don't think you can get into trouble unless you're sort of at the very end of your address space, right? Because you're going to load, when you're loading it, you're just loading the bits. I guess you're wondering if you got like a NAND. No, I don't think you can get into seg fault trouble with this, but we can try to think of a case where you might be able to. I don't think so. The worst thing that happens is you load those bits, it's some weird floating point number, probably a NAN or something like that, and then, it just works. Yeah. Okay? All right, so good. So let's then look at an example. So we're going to do a matrix multiply. So we've got these 2x2 matrices, matrix A, matrix B. We want to get an answer in matrix C, right? So we're going to take a column of A, we're going to match it up with a row of B, and you know how that works. Okay, so the first C11 is going to be A11 times B11 plus A12 times B21. And then the definitions for the other guys are here. And then here's an example. If A was this matrix and B was this matrix, you would end up with this answer, 1, 2, 3, 4. Okay? So we know how to write a sequential program to do that, or a serial program to do that. How do you do it using these SIMD instructions? So that's what this example is. Okay, so our result C is going to be stored in 2 of these big registers. Okay, so and we're going to store it in column order. So so C1 is going to be the answer for that first cell of C. This will be this will be the answer for the first row the first column of C in the second row. And then down here, you've got C for the second column. So first row, second row. Okay? And then we're going to look at, we're going to look at A. And then we've got to multiply a column of A by all of B. Okay? So we're going to use 1 register to store a column of A. We're going to use 2 registers to store all of B. Okay? All right, so, actually, we're not going to use, we're going to play a trick with B, actually. So watch this. Okay, so we start off, we're going to initialize our answer to all zeros. That's what's gone on there. Okay, and then we're going to do our first iteration. So we're going to load, and this is double precision just for this example, so it's two 64-bit quantities. Okay, and so we're going to load that first column into A, okay, using this load intrinsic, PD, right, packed double precision, that's what PD means, okay? And then we're going to use this funny load and broadcast to load up the first row of B. So what that does is it's going to load in register B1 two copies of that 1-1 cell of B, okay? And then in register B2, it's going to load two copies of the second column of B that in the first row, so 1, 2, 1, 2. So you can see what's going on here is we've loaded the first column of A and then two copies, basically, of the first row of B, all right? And we did that using one instruction here, and then we invoked two instructions here, okay? And again, the second instruction is this funny one that's making a copy. So it's putting the same thing in both halves of the register. Okay, it's taking a 64-bit quantity, and it's putting it twice in the register. All right? So, cool. All right, so then we're ready to generate our first intermediate result. So we do an add of what was in C1 before plus the multiplication of A times B1. All right, so what's that's going to do, right? This is SIMD. So what that means is we're going to multiply A11 times B11, okay? And then in the same instruction, right, because it's SIMD, it's parallel, single instruction, multiple data, we're going to multiply A21 times also B11, because we've got it in both places in the register here, okay? So that's going to generate in one instruction this first intermediate result, which is 0, which was what was in C1 before, plus this multiplication, and 0 plus this multiplication. Okay, and that all happens in one instruction. Okay? All right, actually, I'm sorry. The add happens in a separate instruction in this case. There's another instruction that I showed you last time, which was multiply and add. So you could actually do it in one instruction if you wanted. Okay? So is everyone clear on that? That's how we're getting our parallelism. We're doing two multiplications for the price of one, basically. Okay? So we do that. We fill up C2 by playing the same trick with multiplying A times B2. Okay, and we get the same trick there, and we end up with this intermediate result. Okay? So that's cool. All right, so now watch the changing colors. So now we need to do our next iteration, right? There's going to be two iterations because it's a 2 by 2 matrix. Okay, so so we've got to read in what? We've got to read in, I got to get my columns and my rows straight here. We've got to read in the second column of A, and then we're going to play the same trick with B. So we're reading in, we do another load, read in the second column of A, so now we've got A12 and A22 in there. And then we're going to read in B, we're going to read in the next row of B, so we've got B21 replicated and then B22 replicated. Okay, so same exact trick, we just shifted columns and rows. Okay, so great. We then run our adds again, and then we get that intermediate result, and guess what? That's our answer. Okay, so we're able to do a 2 by 2 matrix multiply using, basically half the instructions, or yeah, maybe square root of the instructions. Okay, because we're doing them 2 at a time. Okay, so any questions about that? Because that's the essence of SIMD, and the only thing that's a little tricky about it, so first of all, you're able to call these from C, right, because they're these intrinsics which look like C functions, but are actually, well, I'll show you what they compile to in a second, okay? But the other thing that's kind of curious about this one is that in order to make this work, you had to play this trick of replicating B in each of these registers. Okay? Yeah? Well, we actually told it to here. So this is actually a C statement. So this says, so I'll show you this in a second, but this says C1 equals, right, and this is just a function, these are just a nested function call. So, right, I believe these intrinsics don't, because remember, this is a different instruction set. This is this is the Intel instruction set. So, oh, I'm sorry. So let's just look at the C code for a second, then I'll show you what the assembly looks like. So this is here for your edification. You can look at it later. But here's where we declare all those 128-bit wide variables, C1, C2, A, B1, B2. Okay? We initialize them. So here we're initializing A. If you remember that example, with this, A was just zeros and ones. We initialize B, which was this 1, 2, 3, 4. And then we initialize C, which is our answer. We initialize that all to zeros. Okay, so this is all just C code. All right? And then the action happens here. Okay, so you know, here's where we first load C1 and C2. You know, and then we go through and we do that thing that I just showed you in an animation, where we load the registers, we replicate B when we have to, and then we produce the answer. Okay, and then at the end you actually store the result. Okay, and this is your question. You actually store the result in C1 and store the result in C2. Okay, so what that ends up looking like is this set of assembly code where you've got a loop. You go down and you check the loop and you go through it twice, and then at the very end you store the results into the answers. Okay, so I went through that example quickly, but I wanted to make sure you had it in your notes, that you sort of knew what it was. And then you can go through it and take a look and, make sure you understand how it's working and why it's working. But the fundamental thing that's going on there is we're running this matrix multiply in many fewer instructions because we're able to do lots of things at the same time. And I think just out of pure sort of animation laziness, this was done with double precision. But, if for a lot of things you're going to do it with single precision. So you'd actually be doing these things 4 at a time, not 2 at a time. Right? Because for single precision, it's only 32 bits. You can fit 4 of them in a register at a time. Okay? But this is how it looks in C. You don't have to worry about writing the assembly code, but if you notice, you have to know what's going on, right? In order to write this command, you're basically thinking like an assembler, okay? Because you have to know that that's a pretty thin veneer over the assembly language. But the idea here is that you're focused on performance, right? You wouldn't do it this way if you didn't care about performance. If you didn't care about performance, you'd write it the simplest way possible. Okay, but if you really care about performance, you can get at the low-level functions without having to really worry about, all this stuff. At least you're not, writing labels and doing jump not equals to that label and stuff like that. So it's simpler than that. Yeah? Okay, great question. So what if the 4 things you'd like to operate on at a time are not next to each other? And the unfortunate answer there is to use this trick, you'd have to copy them, put them together, and then use these tricks. So if you really want to do this, use these SIMD instructions to get that parallelism, stuff has to be next to each other. It all has to be sequential in memory. It all has to be together in memory. Okay, and you can make that happen by mallocing some space and moving things around. Yeah. Oh, I'm sorry. Can I just say before you ask your question? But remember, I talked about this last time. A lot of what you're doing these commands for are things like graphics and frame buffers and things like that. And there, it's just a big array in memory, and everything really is laid out next to each other. So for most of the cases where you're doing this kind of SIMD processing, that concern about what if things are spread all over memory isn't really an issue because you're operating on some big multidimensional array. So, okay, sorry.
Does it work on like AMD
Other processors? Yeah. Okay, good. So the question is, am I being paid by Intel, or does this work on other processors too? And the answer is that other processors have their own version of these. So AMD has its own SIMD extensions and its own intrinsics. But they're different. It's not standardized. I don't believe. And the other thing to remember is this is also what's going on in a graphics processing unit. So probably the next time we teach this stuff, we'll switch it to being about these kind of processors to being how do you interact with a GPU. So yeah, so GPUs have their own languages as well. Yeah. Can one processor take multiple instruction sets? Usually not, no.
So then how come our machine
How come your machines are able to run the code, whether it's MIPS or not? Because, yeah, I believe you're running an emulator. Yes. So at some point, remember one of the big ideas is layers of translation. And so we can put a layer in our system that understands this language and compiles that into something that runs on its native language.
Let's say my lowest layer was one core, one instruction, one piece of data at a time.
Uh-huh.
And I tried to write the program in two different instruction sets. One that was like this, and then like normal, one that was like this. You wouldn't see any increase.
Yeah, okay, good. That's a really interesting point. Unless is anyone from any of the TAs paying attention and want to bail me out here? So when you do this stuff in the lab, is it running on an emulator or is it running? I think the MIPS is actually running on an emulator. And yes, and okay. Okay, so that's really so I'm glad we had this discussion. So that's really interesting. You guys have been using MIPS this whole semester thinking that that's the real assembly language, but that's actually not the language that the actual processors you're using are running. It's actually this, which is interesting. Okay. Right. Okay, but the beautiful part of this idea of language translation is at some point you don't really care. Like you didn't care until we started talking about performance and you said, well, wait a minute, why did this speed up? And then you actually care about understanding what's happening at those different layers. But in general, if you have a good abstraction, if you have a layer that's giving you a robust representation of an abstraction, for correctness purposes, it's going to work. For performance reasons, you might have to dig under a little bit and see what's going on. So, and that's interesting. All right, so that's all I want to say about SIMD. So any other questions about SIMD before we move on? Yeah. Okay, the question was, do engineers at Intel just hate their jobs? Do you want to elaborate? So for one thing, they don't have free hamburgers. I know that. Okay, good. So the question is, boy, this stuff is really complicated. And isn't it hard to build these processors? And isn't it hard to get all this stuff to work? And the answer is, yes, it is. And in fact, when Dan picks up the lectures in a couple lectures and starts talking about how this stuff is actually implemented at the lower layers, you'll actually see where having multiple instruction formats and all that starts to really impact the complexity of the underlying processor. So you'll see this. That being said, the market seems to be okay with these things. So Intel manages to get them to work. They don't often have bugs, although every once in a while you hear about floating point bugs. Most floating point work, by the way, gets done in these SIMD instructions. So there are issues with floating point there. But yeah, it is a design choice, and this RISC versus CISC philosophy has been, was a big debate, and it's still not really settled. Okay, good. So question is, well, if a company, let's not use names, but if a company that had a system like this and they weren't worried about legacy, they were just worried about, they wanted to build the best processor, would they start with this? Yeah, probably not. I mean, certain companies that we're not going to name also have other processors that are much simpler than this because they're meant to run in mobile phones and things like that. So it kind of depends on what you're trying to do. I mean, the ultimate test is, if you look at the, I forget what it's called now, but the list of 500 high performance machines in the world. So the fastest 500 machines in the world, you look to see what processors they're running. That's going to give you the answer of whether this stuff works or not. Yeah. Okay, good. So again, a great discussion. So this stuff seems to be resonating at least with the people who are asking questions. Yeah. I'm sorry? Okay, so the question is, does this SIMD code compile on any machine? I don't think so. You have to load the libraries for the compiler, for this processor. And if you're on a processor where those libraries don't run, it's not going to work. Yeah. All right, good. So, okay. So, jump up a bunch of layers. What are we going to do now? So remember, we're looking at all these different forms of parallelism. And we talked about parallel requests. We just spent a bunch of time talking about parallel data in terms of, SIMD and also MIMD. So now we're going to look at a different type of parallelism called parallel threads, where basically we're going to start looking at things across cores. Okay? So we started off, we're kind of jumping around a little bit, and I apologize for that, but we started off talking about parallelism across the different servers in this warehouse scale computer, right? And then we said, okay, let's focus way down and let's look at a single core. Okay, and let's look at some parallelism there. We're actually going to come back to a single core later. Okay, and now we're popping up a layer saying, okay, let's look within a server, what can we do for parallelism across having multiple cores? Okay, so how do we do parallelism there? And that's really going to be the topic of the rest of today and the next couple lectures. Okay, good. So, here's our architecture. Okay, and if you remember, a bunch of classes ago, I showed you sort of the silicon version of this. Let's look at the PowerPoint version. And basically, what you've got is a processor core. You've got a cache. Okay? You've got another processor core, a separate cache. Another processor core, a separate cache. And these are all connected through the interconnection network, which is going to be, actually in the chip, right? Because all this is on a single chip. That talks out to memory, talks to I/O. It's not shown in this picture, but as we discussed before, oftentimes level 1 and level 2 caches are private to a processor, like we're showing here. Level 3 is often shared across the cores. Okay? So, but that's the basic idea. Okay? And so sometimes this architecture is called a shared memory architecture. Okay? Why is it called a shared memory architecture? No mystery. There's one memory, and all these cores use it. Okay? So think about that. That's kind of a cool thing. Okay? So why do we want to do that? Well, we're going to get better throughput if we have multiple threads, multiple jobs. So if you're running a browser and it's a multi-threaded browser, the browser might be doing a bunch of things at the same time. Having when you load a web page, it's actually got a lot of things in there for all the images and the ads and all that. A good browser is being multi-threaded. It'll send all those requests out at the same time. You'll have to deal with them all when they come back. Operating system is multi-threaded or even more. So, there's lots of opportunities for just doing, request-level parallelism like we talked about. Yeah? Oh, ooh, okay. Wow. Okay, boy. Well, so the question is, what's the difference between multi-threaded and multi-process? Or the simpler version is, what's the difference between a thread and a process? So we'll get into this later when we talk about virtual memory later in the semester. But the basic idea is that so a thread is called a thread of control, and that's an instruction path. Okay, so you've got your code. It does this instruction, then this instruction, then this instruction, moves back here. That's a thread. A process contains often multiple threads, and what the process has that's beyond that one, so the two things that's different about a process and a thread is that, first of all, a process can have multiple threads of control in it. Okay, and second of all, everything in that process uses the same address space. Okay, so when I start a process on a machine, if you start a process on the same machine, we both think we own all the memory. That's what virtual memory is all about. So I get an address space that starts at 0, 0. You get an address space that starts at 0, 0. They're actually going to share physical memory, but we ain't going to worry about that for another month. But we'll talk about how that works. Yeah? Can you call a process a program? No. No, no, no. So Dan says yes, but that's because Dan's not a database guy. Okay, so for this, so the purposes of 61C, we'll agree that the answer is yes. When you see me again, if you can't avoid it, in CS 186, the answer is going to be no. Because a program like Oracle, as an example, is made up of a gazillion processes, okay? But for the purposes of this course, Dan's exactly right. If you take your C code and you compile it, and you get an a.out, and you rename it, because you're not supposed to call it a.out, and you run it, that's going to run as a process. Yeah. Okay. Okay, one more, yeah.
Okay, I don't understand why it's possible to have more threads than processors if
Oh.
juggle around with the threads.
Okay, so the question was threads and processors. So why can I have more? Oh boy. So, yeah. Thread of control. Yeah. Okay. Okay. Good. Okay. So the question was, I don't understand how I can have more threads than processors, than physical cores, let's say. And the answer is, remember, you're running your program. We're trying to do our best with memory access, keep things in cache and so on. Every once in a while, you do something really dumb, like you access a piece of data that's not in the cache. You pay 100 clock cycles for that, okay? Sometimes it's not even in the cache, and you have to go out to disk, and you pay 100,000 or more clock cycles for that. So the question is, what's the processor going to do while you're waiting for the system to go out to Pluto and get the data? And the answer is it's going to run on some other thread. So you can have lots of threads, but at any given time, each processor there's an active thread. Okay. Wow. Yeah. Oh, boy, okay, boy. We're going to go through all of computer science here today. So the question was, does the processor only switch threads when there's a blocking operation like an I/O or cache miss, or does it do that anyway? And the answer is, there's actually both flavors. It's called preemptive threads and non-preemptive threads. So preemptive thread means you're running, but you could lose the processor at any time, okay? And as you can imagine, programming with preemptive threads is harder than programming with non-preemptive threads, because you have to, in a preemptive thread, you have to realize that you might lose the processor at any time, right? Where a non-preemptive, you only lose the processor when you give it up, okay? All right, good. So high throughput, and then, sometimes we'll take a single program, to get to your question about program versus process, and we'll split it into multiple threads, like a browser, okay? And then you can run those threads in parallel, so you get to speed up that way, okay? So we're going to call these processes cores. So a lot of times when we talk about how big a data center is, we'll say, well, it's got 10,000 servers, but it's got 80,000 cores, okay? And the number of cores is the number of physical threads of control you can have running at a given time. Okay, this graph is awesome. I love this graph. If I was Dan, I'd be saying, love it. It's hard to do. I love this graph. I love this graph. So let's so let's look at this. I would also probably play the Godfather music too. But anyway, let's. Oh, and by the way, I would also have a clicker question. And Dan's been giving me a hard time about that. So I promise everybody in this room, and for all your friends who didn't come yet to here, tell them to come on Friday. We'll have a clicker question. And bring your clickers. Okay, today we don't have one. All right, what is this admittedly somewhat complex graph showing? So it's very cool. This is showing, so we've got a timeline here, and we've got a log scale, right? Power is a 10. So this is showing, how many cores did a typical chip have, okay? And you can see from the beginning of time until about 2005, when you bought a processor, it had one core. So we never even talked about cores, because when you bought your 8086 chip or whatever it was, or even your Pentium 2, it had one processor, one core in it, okay? Now, after 2006, that started changing, and you can see that we're on this new trail, this new track, where the number of cores is like doubling. I forget, it's on the next slide, but it's doubling every year, every couple of years, okay? So number of cores is going up. So when we first designed this course, back before you guys were born, and maybe even before some of your parents were born, we didn't talk about parallelism much, because it wasn't a big deal. But now you see, after 2006, you can't buy a processor. You can't buy a chip that's only got one processor on it, okay? So why is that happening? And that's why this graph is so cool. So this is showing you kind of what's happening. So you can see this red curve is the power in watts that a chip usually took. And what was happening is And this green line is the frequency. So how fast, right? Remember we talked about clock ticks, and you went from 1 gigahertz to 2 gigahertz to 3 gigahertz. That's what this green line is. And so in order to get computers to run faster, we were trying to get those clocks to tick faster and faster and faster and faster and faster. As we're doing that, the energy consumption of that processor is going way up, okay? So what was happening is the amount of energy required to power a chip was just going up and up and up and up and up, and also the heat and all that. So what happened was people said, all right, we can't keep making the clocks run faster, right? We went from 2 gigahertz to 3 gigahertz. Maybe we can go to 4 gigahertz, but at some point we can't make it go faster because this thing's going to melt, okay? And it's going to consume all the energy we have. And so meanwhile, at the same time, see, this is why this is such a great graph. You could do a movie about this graph. This is showing Moore's law, right? That's the growth in transistors per, some unit size of silicon, right? And you can see that's just going up and up and up and up and up. So what happens is you start hitting the energy wall here, and you go, okay, I need to make my system go faster, okay? But I can't make the clock go any faster. So what am I going to do? Well, I still have all these transistors, so what am I going to do with them? Oh, I'm going to start putting more cores on my chip. So if you're wondering why we have to worry about multi-core when, even as early as, as recently as 5 or 6 years ago, we didn't have to worry about it, that's exactly why. Okay, so we're trying to get machines to go faster and faster. We've hit sort of the power wall and the heat wall, and so, but we've still got plenty of transistors, so we're going to use them to put more processors on a single chip. Okay, and that's why we're talking about this stuff. All right? So, that's the cool graph. All right. So, okay, so what that means is we've hit this wall. The only way we're going to get things to go faster is to have more parallelism. Okay? So, we're now living in a world where two things are happening. It's actually kind of interesting because remember, Moore's law is still working. We're still getting more and more transistors. So what's happening is the width of those SIMD registers is doubling every 3 to 4 years. Okay, and you saw this in our slides because originally that XMM, I forget what it was called, the thing that was before SSE, that was 64-bit. Was it MMX? Thank you. That was 64 bits, right? Those registers were 64 bits. When we went to SSE, the registers became 128 bits. Very soon, they're going to be 256 bits. All right. Why does that matter? Because remember, we operate on that whole register with one instruction. So if you can put twice as much stuff in that register, you're going to get twice as much parallelism. Okay. So for the same cost of running an instruction, you're going to operate on twice as much data. So the SIMD registers are growing wider. Okay. Second thing that's happening, and the other thing we're using all those transistors for, is the MIMD story. That basically every 2 years we double the number. We add 2 cores. Okay, so that's interesting. So that's why you started off with the core duo, and then you ended up with the dual core double duo, core 2 duo, and I don't know. You got to hire some new marketing people. But basically, every 2 years you're going to get 2 extra cores. So you guys can figure out when you graduate. Some of you guys are going to have machines with 16 cores. Some of you maybe 32. You can sort of plot that out. Okay. Some of you maybe only 8. Okay. So that's the world we live in. And so the question is, how do you exploit? How do you use all this parallelism? We talked about one way of using these SIMD instructions. We're going to talk about another way now, which is using the multi-core processing. And this is what we're doing in labs, and we'll be exploring this in the rest of the projects as well, at least in the next two, the current project and the one after. All right, so this is in your notes. I won't go over it, but if you take the growth in the width of the SIMD registers, and you multiply that times the growth in the number of cores, you get this kind of speed up and sort of peak, double precision floating point operations. Okay, so even though we hit that power window or that heat window, that wall, even though we can't make the clock tick any faster, we're still going to get better and better performance, and it's because of these two trends. The number of cores growing by 2 every 2 years, and the number of bits growing in the SIMD registers. Okay, so good. So computers are going to keep getting faster. All right, so now we've got this situation where we have multiple cores. They're all sharing the data. So how do they share that data? How are they going to coordinate? Right, because if I've got a word and I update it, and you want to read that same word, do you see my update or not? Right, things get complicated. So how do they coordinate, and sort of how does it scale? How many cores can you really get to work on one of these systems? All right, so we're going to talk about, like I said, a shared memory multiprocessor, SMP, and the way the shared memory multiprocessor works is that there's one memory space, one physical memory space, and all the processors use it. Okay, so if I read the word that's at location 256, and you read the word at location 256, we're going to read the same word. Okay, that's what you want to happen. Okay, and the way one thread on one core talks to another thread that might be running on another core is by taking advantage of that shared memory. So if the two threads agree on a variable, that there's a variable that they're both going to use, they can communicate by reading and writing that variable. Okay, so if I have, if we have a little flag that we want to, that I grab it and then you can grab it, then I can set the flag, and when I'm done with it, I can release the flag. When you want it, you can set it. If, you check it to see if it's free. If it is, you grab it, and we can communicate that way. All right, so shared variables. Like the mailbox flag, very good. Okay, like the mailbox flag. Okay, so I'm going to give you a very quick view of how one of these algorithms might work, and then we'll drill down next time. All right, so let's say you had 100,000 numbers you want to add up. You had 100 processors to do it. Okay, how would you do that? How would you parallelize that? Okay, well, you guys have already seen MapReduce, so it's probably kind of in your mind, kind of the pattern that you'd use. Okay, but this is a little more direct. All right, so what we're going to do is we're going to say we've got 100 processors. We're going to give them IDs, 0 to 99. Okay, then since we have 100,000 numbers and 100 processors, we're going to partition our data set. So every processor gets 1,000 numbers. Okay, remember our goal is to add them up. Then we're going to do this initial phase where on each processor, right? So we're going to do this 100 times in parallel because we've got 100 processors. Okay, we're going to add, each processor is going to take the 1,000 items that they're responsible for and add them up. Okay, so you take your processor ID, you multiply it times 1,000, and then that gives you the first number that you care about, and then you add up the next 1,000. So if your processor 0, you add up from 0 to 999. If your processor 1, you get 1,000, and you go up from there. Okay, so in this first phase, 100 processors all chugging away at the same time, take 1,000 numbers and compute their sum. Okay, so that's completely parallel. But now you have to do the reduction phase. That was now you got to do the final reduction. So now we're going to go into the second phase. We're going to add up all those partial sums. Okay, so the way we're going to do it is we're going to say, okay, we'll do it pairwise. We'll have half the processors add pairs, and then we'll add them up 2 at a time. There's other ways to do it, but this is the way we're going to do it here. So here's a program for doing that. There's 2 things to know about this program. Let me just build it, sorry. So every processor is going to run exactly this program, okay? So you have to know your processor number, right? That's PN. That's something that's private to each thread knows its, the processor number that it's running on. Okay, and what you say is, okay, everyone's synchronized. Great, now let's start. So this blue stuff is a corner case, which is what if the number of processors is odd. Okay, who handles, right, you're doing things pairwise, there's going to be one left over, who handles it? And our answer is processor 0 by default was going to handle it. So if the number of processors, right, mod 2 is not 0, that means it's odd. And if your processor 0, that means you're going to be responsible for this guy. All right? That's an edge case. Everyone else just says, okay, I'm going to take my processors, I'm going to split them into the lower half and the upper half, and basically the upper half is going to send their data to the lower half. Okay, so if you're in the lower half, you're responsible for adding your stuff plus a partner from the upper half. Okay, and you do that and you reduce it by 2 every time. Okay, so I'm going to show an animation, and then we'll go over this again next time. So here's how it's going to work. So let's say you had 10 processes instead of 100. Okay, so in the first phase, we say, okay, we're going to divide it in half. The upper half is going to send their information to their partner in the lower half. So that all goes this way. So each of these processors, 0 through 4, adds up their data plus their partner's data. Then we're going to split it in half again. Okay, well, 5 divided by 2 is odd. So what do we do with P4? That stuff goes to partition to processor 0. Okay, we're back down to 2. We split that in half. They both go to processor 0, and now we've got our answer. Okay, so what we're able to do is do all those additions, right? 100-way parallel, and then we need a way of putting them all together, and this is a simple way to do it. So with that, I will. Okay, well, sorry. Let me leave you with just a challenge, which is think about now. Remember. Oh, sorry. Just give me a second. I'll let you out here in a second. Promise. Remember, everybody's running this exact code, okay? And everybody's running in the same memory. So how does this work? How do we get that to work? That's the challenge that we're going to talk about on Friday, and we're going to have a clicker question too. All right, thanks.